Hello, welcome to our second session, and in this session we're going to do a little bit of review. We're going to talk about free fall, Newtonian mechanics, equilibrium, and then we're going to talk about electrical transport and mobility. And to start off, I'd like to share with you what I consider a beautiful rendition of Una furtiva lacrima by Donizetti from his opera Illici d'amore, the elixir of love. One of my favorite performers, I should say, Helmut Lotti. So enjoy, and we'll see you in a few minutes. Okay, welcome back, and let's just do a real quick review. Last time we said that the energy has the units of joules, and it's equal to RT. R is the universal gas constant. T is the temperature in Kelvin. This is in our world, the big world of flasks and balloons and things like that. In the atomic world, instead of R, we use K, Boltzmann's constant, a very small number, still the same units. It's in joules, but a very small value. So in order to make it a reasonable value, we divide by an arbitrary constant. In this case, we pick the charge of an electron, 1.6 times 10 to the minus 19th coulombs, and then we get this famous number 0.026, but it's not in joules, it's in electron volts, and that's an important number that we should remember. So if you're talking to somebody and you're not quite sure what his profession is, this is a good test to see if he's an engineer. Ask him the following questions. Mr. So-and-so, do you know your wife's birthday? Oh gosh, I didn't know my wife had a birthday. Okay. How about your wedding anniversary? My wedding anniversary, forget about it. Oh, do you know the thermal energy of an electron at room temperature? Well, that's easy, 0.026 eV. So if you get answers like that, you know you're talking to an engineer. Okay, I just want to review very quickly also the Maxwell Boltzmann distribution. I derived this in the session summary. It's got two components. It's got a parabolic component and an exponential component. And it has a constant which is only a function of temperature. For very low velocities, this value on the exponent is approximately 0. V is close to 0. So it's e to the minus 0, which is 1. So that just goes away. And we just have a parabola for very low values, which is a function of, I should say, the coefficient is a function of t. For small t, this is a big number. I just pick out of my hat, say 2. For high values of t, high temperature, hot, this is a small value, and for arbitrarily, I would say 1/2. So let's take a look at these two curves. This is the steep curve, the 2, and this is the sort of shallow curve for the hot. They both have exponentially decreasing decays, but they have different characteristics for low velocities. For zero velocity, and this is perhaps not quite intuitive, they have 0 number of particles. And I just want to take a look at that in a little bit more detail. So let's take a look at a particle. Here's a little particle right here, and I'm claiming that in order for this particle to have 0 velocity, if it's hit from the right to left by another particle, it must be hit at that exact same time by a particle going from left to right with the same force and exactly the same direction. And that, folks, is essentially impossible. I didn't say impossible, but essentially impossible. There are only two absolutes in the world, and they are birth, which is absolutely impossible, and death, which is absolutely certain, but those are theological concepts. Everything else is possible, including the possibility of this table spontaneously levitating and hitting me in the chin. But I don't have a chin guard, so I'm not really worried too much about that. Possible, but not very likely. Okay, so let's now look at Newton's second law. Newton's second law states that the force on an object is equal to its mass times its acceleration, and its acceleration generally we're going to take as a constant. Could be 0 if it's in free fall. If it's in space close to the Earth, the acceleration is a constant at 10 meters per second squared. The units of force are mass, which are kilogram, times the units of acceleration, which are meters per second squared. We'll talk about that a little bit more in detail in just a couple minutes. Anyway, the energy of that same particle is equal to force times length, which we saw in the previous session. So it's kilograms meters squared per second squared, and that is the units of energy, and that's true in the mechanical world and in the electrical world. Let's check it out. For kinetic energy, it's mass times velocity squared. Mass kilograms, velocity squared is meters squared per second squared. Check. Gravitational potential energy, force, which is ma, but m, of course m is in kilograms, a in close to the Earth is g, 10 meters per second squared, multiplied by meters. This y here is meters, so it's kilograms a meter per second squared, and that also checks out. Electrically, it's equal to the electric force, or the electric field, which we're going to see has units of kilograms per meter squared, because it's a force, and that's multiplied by y, which is in meters, also kilograms meters squared per second squared. Let's talk a little bit about units and equilibrium in free fall. So I'm going to sacrifice myself for science, and I am going to fall off or jump off of the roof. And the roof is about 4 meters high, and I'm going to ask the question, how long does it take me to hit the ground? Well, let's just make a simple equation. Y equals Vt. The units of y are meters, units of velocity are meters per second, time is second, units check. The equation is good, except it's irrelevant. And the reason it's irrelevant is I know y, but I don't know v, and I don't know t. Well, you can say, well, I know v, I'm jumping off the roof. Well, my velocity when I first jump off the roof is 0. I haven't started to fall yet. When I hit the ground, I'm not going to have a 0 velocity. I wish I would, but I'm going to have a velocity much higher than v. So the equation is correct but irrelevant. So why don't I just then multiply it, or instead of taking y equals vt, take y equals at. Then I've got meters per second squared times meters. I know a is constant. Everything's looking good except the units don't match. The units of a are meters per second squared. Units of time are second. So the units do not match because meters on the left side do not match 1 over seconds on the right side. So how to get around that? I just square t. So now I have y equals at squared, and then the units match, and that's the correct equation, except there's a pesky little value of 1/2, which in order to be exactly correct, I'm going to put that in there. And I can solve now for t, and I get 0.9 seconds per squared. We're tempted to write then that v equals yt, but that's not correct because I know y and I know t, but this doesn't give me the proper v. This gives me the average velocity. 0 on top when I first start, 9 meters, well, we're going to find it's 9 meters per second when I hit the ground. So if I solve for the final velocity, I get in fact 9 meters per second, or I can use the equation v equals at. This equation is also good because I have meters per second on the left side, and I have meters per second squared times meters per second on the right side, and I get the same value of meters per second. How large is meters per second in miles per hour. Well, what I do here is I simply convert from meters per second to miles per hour. So meters on the bottom, meters on top, cancels out. I get kilometers on top, kilometers on the bottom, miles on top, kilometers cancel out. I get miles on the bottom, on the top, excuse me, seconds on the bottom, seconds on the top per hour, 3,600 seconds per hour. Multiply that all out and I get about 20 miles per hour. That is about the velocity one would find in riding a bicycle at a reasonable rate. So if you fall off, God forbid you should fall off a bicycle, but if you fall off a bicycle, it's about the same as hitting the ground jumping off a one-story building. So the lesson, always wear a helmet. This is equivalent to about 0.33 miles per minute, or about 3 minutes per mile, which is well under the fastest rate that a human can run, which is about a mile in 4 minutes. Now let's see what the limits of human performance are. And in this case, I'm going to consider the 100-yard dash. So the 100-yard dash can be performed in about 10 seconds. Disclaimer, not by me, and I would emphasize that. So let's figure out what that would be in miles per hour. Well, 10 yards per second, there are 3 feet per yard. There are 5,200 feet per mile. All that cancels out, giving miles on top. Again, 3,600 seconds per hour gives about, again, 20 miles per hour. So if I could continue, or somebody could continue, running a 100-yard dash in 10 seconds, and he or she could continue that for a mile, he would be able to run a mile in less than 3 minutes. Now I'm going to skip over this part here, but I just want to emphasize one issue here. In free fall, or in space, acceleration is constant. It's actually equal to g. The velocity is linear, v equals at. The distance is parabolic, y equals 1/2 at squared. That has an analogy in the electrical world for electric charge density constant. If electric charge density is constant, the electric field is linear and the voltage is parabolic. Okay, now let's try to increase the distance. So I'm going to end it all. This is me. I'm going to jump off the top of the Empire State Building. Okay, so in theory, the velocity should increase by 10 meters per second every single second. So after 1 second, it's 10 meters per second. That's what we found when I jump off the one-story building. It takes about 0.9 seconds. If it took 1 second, my velocity would be 10 meters per second. After 2 seconds, it's 20 meters per second. After 3 meters, 30 meters per second, etc. Every single second, it increases by 10 meters per second. That's why the units are 10 meters per second per second. The force is my mass, which is about 60 kilo, times the gravitational constant. That doesn't change. Force is the same. The gravitational acceleration is constant. What does change as I jump off the Empire State Building and I go down and down and down, there is a resistive force, a buoyant force, which pushes me up. That buoyant force for a given area is proportional to the velocity. So it's 0 up here because the velocity is 0. As I start picking up velocity, that buoyant force increases more and more until it comes to a point where the buoyant force is equal to the gravitational force. At that point, I am in what I would call equilibrium. There is no net force. There's an upward force due to the buoyancy. There is a downward force due to gravity, and that takes somewheres about 3 to 4 seconds. To jump off the Empire State Building would take much longer than that. Whether or not there was if there was no buoyant force, it would still take, I don't have that calculation, but I think it's about 15 seconds or so. After about 4 or 5 seconds, I reach a terminal velocity of about 100 miles per hour. Still quite a bit, and enough to do a lot of damage to me personally. Well, as I'm falling off, I have in my hand a little feather, and this feather is also subject to gravitational force, mg. But its force, its gravitational, I should say it's subject to a gravitational acceleration, g, but its force is much less because its mass is much less. Its mass is orders of magnitude less than my mass. For example, fractions of a gram. So once it hits a reasonable velocity, in fact a very small velocity, the buoyant force will be equal to the gravitational force, and after that point it just floats down. So for me to reach this equilibrium, buoyant force equals gravitational force, it may take about 4 or 5 seconds. For the feather, it takes a fraction of a second because of its lower mass. Now let's look at a video clip of a case where there is no buoyant force at all. Free force with no, I would say, collisions, maybe is a little bit harsh word. There's no force which forces me up. Okay, so this is a steel ball, probably about 15 kilo, maybe 30 pounds or so, and this is a little feather, and they're going to be dropped, and they're going to be dropped in a high vacuum. About 100 feet or so, they're going to make a trajectory. There is no buoyant force because there are no collisions. There's no atmosphere here. It's been evacuated. So let's see what happens as the steel ball and the feather drop in a vacuum with no buoyant force. And here they go. You see they're starting out the same. They'd start out the same even in atmosphere. But as they fall at the same rate because their accelerations are the same and there's no buoyant force pushing up on either one. They do, however, have very different forces when they hit. And here they're about to hit a boom. And you'll notice that the steel ball hits with much greater force because it has much greater mass. Its mg is much greater than the mg of the feather, but they hit at the exact same time. They have been speeding up as they make their trajectory from the top to the bottom, and each second their speed increases by 10 meters per second. One other thing, before we get to that, I should say, let's say, and I didn't draw me in here, let's say I'm in an airplane and I jump out of an airplane, and now we're not talking about 1,200 feet of a trajectory, we're talking 5, 6, 7, 8,000 feet. And it still takes about 5 to 10 seconds. I reach a terminal velocity. And what do I do after that? I pull the string on my parachute. Except, oops, I forgot my parachute. I knew I forgot something. Well, I'm looking down at a concrete parking lot. This is not good, but I have one more trick up my sleeve. I snap my fingers and I'm able to turn off the buoyant force. Now, if I turn off the buoyant force, I'm still falling at about 100 miles per hour, but now I've got a force which pushes me up. So what happens? Well, what happens is I slow down. As I slow down, the velocity becomes less, my downward velocity becomes less, the buoyant force becomes less. And it's a spiral. It's a good spiral. Lower velocity, lower buoyant force, lower buoyant force, lower velocity, until I reach a point where I hit a velocity of 0. I am suspended in midair. Now you think, well, that's kind of crazy, but that's exactly what happens when you're going 60 miles an hour and you put your foot on the brake. There is not the buoyant force, it's a resistive force due to tire resistance and air resistance. And what happens eventually is that buoyant force, or no, I should say not buoyant force, but resistive force stops the car. It might take a while, but you don't generally have to use your brakes. The buoyant force itself, or the resistive force, will stop your car. Okay, now let's rotate things so we're on a horizontal plane and we're driving in our car and we accelerate to 60 miles per hour. And if you're driving a Tesla, that takes about 3 or 4 seconds. Wow, pretty fast. So the acceleration can be reasonably found. It's the final velocity minus the initial velocity divided by the time, and we get about 9 meters per second squared, or about 0.9 times the gravitational force. That is a huge, or gravitational acceleration. That is a huge acceleration. And if we're in now a constant velocity, for example, we use a cruise control, the velocity is constant, but are we in equilibrium? Now, if I'm in free fall and the buoyant force is equal to the gravitational force, I claim we are in equilibrium. Here, however, I claim we are not in equilibrium, and I'm going to reason that eventually we're going to stop, because eventually the gas is going to run out, and eventually I will get to a point where the car no longer is able to run at constant velocity. And that is the model that we're going to use for ohmic conduction in a semiconductor in silicon. Before we get to that, let's look at another example of an equation which we're going to use quite a bit, which we can derive only using units, and that is a wave. And here we have a sinusoidal wave, goes up and goes down. And I'm going to use the definition of velocity. Velocity is equal to the distance divided by time. For a wave, the distance is the distance from the start to the finish of the wave. Of course, the wave keeps going on, but this distance here is one wavelength, and that is equal to lambda. We call lambda the distance of the wave in wavelengths. The time is the time for the wave to travel one wavelength, and that we call the period, and that we denote that by t. And the units of t are seconds. I was going to say seconds per, no, it's just seconds. And 1 over seconds, I should say seconds per cycle, or seconds per wavelength. 1 over that, the inverse of t, is just cycles per second, and that's what we call the frequency. So 1 over t is f, and then we have that the velocity of the wave, which for electromagnetic wave, it will be denoted as c, about 300,000 meters per second, is equal to the wavelength multiplied by the frequency, and that is a very important equation which we'll have a lot of use for. Finally, let's look at circular motion in a horizontal plane. And here we have a constant velocity. We have a mass which is spinning around an axis. The radius of the trajectory is r, and the velocity is constant magnitude of v, but there is an acceleration, because if there were no acceleration, the mass would fly off at a constant direction, so it always has to be pulled in so that the direction of the velocity changes, therefore there is acceleration, and we're tempted to write that the acceleration is proportional to the velocity, and that of course makes sense, but acceleration is meters per second squared. So what do? Well, we need a seconds per squared on the bottom, so square the v, just like before we squared the t, and now we have meters squared per second squared. Well, it's still not right because the units of acceleration are meters per second squared, not meters squared per second squared. So we have to divide by meters to get rid of the square term. And a convenient parameter to do that would be dividing by r. So now we have a meters per second squared is equal to v squared meters per second squared divided by meters, and the units work out, and it works out that that is indeed the acceleration of circular motion in a horizontal plane, and the force, which in this case is the centripetal force pushing in toward the center of the circle, is just equal to the mass multiplied by v squared over r. Okay, finally let's go back to our equation which we derived in the last section. The current density in amps per square meter is equal to the number of charges per cubic centimeter multiplied by the electronic charge, 1.6 times 10 to the minus 19th coulombs, multiplied by the velocity. That's a general expression. Now what I'm going to claim is, just like a car which is traveling at a constant velocity, the force is proportional to the velocity. Not that the force is, well, the force we know from Newtonian mechanics is proportional to the acceleration. However, if one is limited by collisions, the force is proportional to velocity and not to acceleration. Now let me go back to our car example, way back here, and I'm at 60 miles per hour after about 3 seconds, and I'm doing great, driving along, but I want to go faster. I want to go to 90. So I step on the gas and I go to 90. I accelerate a little bit, but that acceleration from 60 to 90, which can take only a second or less, I neglect. And then I go 100, a little bit more force. The force is approximately proportional to the velocity, not to the acceleration, because the buoyant, or the resistive force, I should always remember to use resistant force rather than buoyant force in a horizontal plane, is going to be so high that the acceleration we can basically neglect. Now it's the same thing, by the way, for a guy who's running. Where was that? Back here someplace. A guy was running someplace back here. He was running a 100-yard dash. We don't consider the acceleration. The acceleration takes place in the first fraction of a second, and after that the velocity is approximately constant at about 20 miles per hour. Well, it's the same thing here. The force, if one is already at a high velocity with a high resistive force, the force is approximately proportional to the velocity rather than to the acceleration. Now let's say I keep pushing it. I keep pushing as hard as I can. What happens? I go to 100 miles per hour, 110 miles per hour, 120 miles per hour. Eventually, no matter how fast that engine is turning, it's 8,000 RPM, 9,000 RPM, it just can't go any faster. We reach a point where the resistive, almost going to say buoyant force, where the resistive force is so high that no matter how much force we try to propel the car forward, it simply cannot go any faster because the resistive force is just too high because the velocity is too high. We say in those conditions that the velocity is saturated. The same thing happens electrically. There is a region in which the velocity is proportional to the electric force, just like the velocity is proportional to the force on the gas pedal in a car, and that proportionality is linear. And then there is a region in which the velocity saturates. We just can't go any faster. The particles, the electrons, the holes simply cannot move any faster. The proportionality, and this is the region we're going to be interested in, it's called the ohmic region. The ratio of the velocity to the electric field is called the mobility. A large mobility, which is desirable, gives us a large velocity for a little bit of electric field. Small mobility, not so good. Small velocity, even if the electric field is large. In all cases, however, the velocity saturates. Now, velocity saturation is a big deal, and there's good news and there's bad news. The bad news is that it's very difficult. In fact, we have no analytic curve for this. So to deal with this analytically, we break it up into different regions, and it's a bit cumbersome. So the mathematics can be a little bit difficult to deal with. The other part of the bad news is that it is a performance killer. It is prevalent in every electronic device that we know, and it murders the performance. Well, what's the good news? The good news is we don't have to worry about it until we talk about second-order effects. Second-order effects in field effect transistors. Anyway, let's put all this together. The velocity now is proportional to the electric field. Force proportional to velocity. That is the critical ohmic condition. The electric field is in volts per meter, volts divided by length. And now we have J, which is equal to current amps divided by the cross-sectional area, the width times the thickness, which is equal to V divided by L. We bring up the WT, and this is Ohm's law. And I'm going to show in the session summary that we know Ohm's law is V equals IR. All of this stuff in here is 1 over R. So let me just circle that. This is 1 over R, and we'll show that the units all work out, although it certainly seems like it's relatively messy to prove that, but it's really not very difficult at all. Okay, so now we have mobility, and we introduced mobility. We'll talk about its units a little bit later, but in order to put it in our hearts, here is a song about mobility, and when I think of mobility, I think of that wonderful aria, La Donna Mobile, by Giuseppe Verdi from his opera Rigoletto. Women are mobile, so let's enjoy that.
Sempre una labile, leggiadro viso, il fiato il riso, pensier. È sempre misero chi a lei s'affida, chi le confida, mal cauto il core, pur mai non sentasi felice appieno chi su quel seno non li va amore. La donna è mobile, qua più malevento, muta l'accento e di pensiero, e di pensiero,
And we'll see you next time.